Good morning, dear students. Welcome to this session on pre-stressed concrete. Uh, till the last session, we have talked about the analysis of pre-stress. Just to present you once again what we have in this unit 2. So we are talking about analysis of pre-stress. We have calculated resultant stress at a section by simple superposition of the stresses from pre-stress, like direct stress from pre-stress and bending stress from pre-stress, also bending stress from dead load and bending stress from live load. Those are the things done, and we have also be able to calculate resultant stress through the pressure line concept, that is 2.3 we have talked about, and also the other concept which can be used to properly uh, to choose the tendon profile correctly for the balancing of loads which will come onto the member. So that is what is called concept of load balancing also we have talked about. Now we are ready to discuss these topics, like stresses in tendons is the today's session, and we'll take 1 or 2 sessions to complete it. And the cracking moment is the last content in this unit, right? So that's about the things which we need to talk about. Okay, so let us see the stresses in tendons to talk about today's session. Right. So stresses. Be sure that what we are now concentrating on the stresses in tendons, not in the concrete. Okay. It was till the last session. Uh, Maybe the superposing the stresses from different aspects and pressure line concept and load balancing concept. All these are to calculate the stresses in concrete. Now this is about stresses in tendons. Okay, so uh, the what is a need for talking about stresses in tendons? Because though you are pulling the tendon and you are getting a value of pre-stress in the dial gauge, or maybe a digital form, but still we need to talk about the stresses in tendons. Reason is about, like a pre-stressed member undergoes deformation due to the action of pre-stressing force and transverse loads acting on the member. Say for example, take this beam, whatever is given here. So while you now pull the tendon, the member is straight and the tendon is straight. Okay, the member is straight horizontal and the tendon is also horizontal while you pull the tendon. Okay, once jacking operation is done and you release the jock, okay, then the tendon starts transferring stress to the concrete. Then what is going to happen, the beam is going to bend like this, right? Hogging. Okay, maybe I'm exaggerating a bit, but it won't be seen actually with your naked eye, but okay, the strains will be very small deflections. Okay, but to understand the concept, I have just made it to look like it is hugging, right? So when you have a member bent like this, the tendon also follows the profile of the beam, I mean, like this. Okay, so what is happening to the tendon? Tendon is also being stretched, so it is elongated, right? A straight tendon, when it is bent, it meant it is meaning that the length of the tendon is increased, right? So which means there is a strain, additional strain than what you created by pulling it. Okay, so you have induced some strain by pulling the tendon. Again, by once you release the tendon from the jock, it is going to transfer the stress to the concrete. The concrete is going to bend because of the no eccentricity that it is having. So because of that, it is going to, due to the stresses in concrete, it is going to bend in the hogging manner. So due to that, the tendon also bends, which means tendon is also developed additional strain. So this is till the pre-stressing operation is done. Once this member is transported to the construction site and it is placed in its position in the structure, then it is going to have some live load and dead load acting on it. In that case, what happens again? It is going to bend down like in sagging manner. Again, the tendon is going to bend, along the profile of the member. Okay, so this is the tendon again. So it is going to bend again in the inverse direction, sagging. So it is going to have again some strain developed. So whatever pre-stressing force that is being induced is not the value that you have, or the stress in the tendon is different from the tendon stress what you feel later on, means after the pre-stressing and after the loads. Okay, so there is a need for talking about stresses in tendons. Okay, that's a reason why we are talking about stresses in tendons. Okay, so let us see. Hence the curvature of the cable changes, there will be slight variation of stresses in the tendons. There will be very slight variation of the stresses in the steel. Okay, right. Considering a concrete beam of span L, the beam which is shown here, pre-stressed by a force of P at an eccentricity of E. Okay. The rotation of the tendon at the supports, the tendon is rotating at the supports, this like this. Okay. Due to hogging of the beam, uh, can be obtained by applying Morse theorem. You have a lot of uh, ways to calculate the slope of this no, tendon, the theta value. Okay, slope of the beam is nothing but the slope of the tendon. Okay, as concrete bent, I mean beam rotated at the ends, the tendon also rotated. Okay, so because of rotation of each cross section of the beam, tendon also being rotated. So when you find this theta value, you will know the rotation of the tendon. So that is done by Morse theorem. You can use any concept that you uh, uh, what you have used earlier to calculate slope and deflection of a member, right? Like there are other methods called double integration method, area moment theorem or Morse theorem. Okay, or conjugate beam method, graphical way of finding it. Like, so there are ways to find slope and deflection of a member. Okay, so here we are using the Morse theorem 1 and 2. Okay, for uh, getting the slope of the tendon. So here just the tendon is plotted along with this initial diagram. So this is the slope that you want. So bending moment diagram for this case is, it is like uh, moment acting on this is P into E. This is P into E. Similarly, bending moment here at this end is also P into E. this we have discussed in detail why this is creating pure moment case, right? The load, when you transfer it to the center, you will get load and moment. Same here, load and moment. So now you have a beam, a simply supported beam with moment at the ends like this, applied moment at the ends m. So bending moment diagram for this is a rectangle. Okay, P into E is the value of bending moment at both the ends. P into E. Okay, this is L, right? So this is BMD, which we will be using for finding slope value. So to find slope, you have to know use area moment theorem 1. What it says is choose any 2 points on the member. Choose any 2 points on the member. So the difference of slopes of those 2 points is equal to M by EI diagram area between those 2 points. M by EI diagram area between those 2 points. So what I'm choosing here is the midpoint of the beam where the slope is 0, because if you draw the tangent here, it will be a horizontal line. So theta is 0 at the midpoint because of symmetry. Okay, and the point A here is having a slope of theta p. Okay, so I have chosen 2 points where midpoint and the support point. So between these 2 points, our M by EI diagram is half of the rectangle. Okay, so M value is this one, P into E, M by EI diagram. So prepare M by EI diagram. Okay, so now the formula for finding this theta is theta C minus or difference, whatever you write, you can write it. So theta C difference theta A or minus theta A is equal to the angle between, difference in angle between these 2 points is equal to area of M by EI diagram. The area of M by EI diagram is only half of the rectangle, right? So area of that rectangle, what is base value is L by 2, height is P E divided by EI. Okay, so what is theta C value? Theta at center, this is like difference. So theta at center is 0. Theta at A is equal to theta P. So theta P value is nothing but PEL by 2EI. That is how you get this value, right? So this is by the very fundamental concept of slope calculation by Morse theorem 1. Okay, right. This is for pre-stressed. After pre-stressing, how much is the rotation of the tendon? Okay, right. Same way, you can find when load is acting, like dead load and live load is acting on the member. Okay, so in that case it is going to bend down like this. So the BMD for this is a so take again a simply supported beam where UDL is acting on this. So BMD is going to be parabola. Okay, because of UDL. Okay, so this value of bending moment is WL square by 8. Okay, this is WL square by 8 value, and this is L by 2 span. Same logic, pick a midpoint on the member and pick the support point. The difference in angle between these two is theta 1 minus 0, because the tangent, if you draw at the center, it is going to be horizontal. So this point will never rotate. Okay, only the other points will rotate, and that is nothing but the slope of that this section. Okay, so theta 1 value, if you want, area of m by ei diagram of this portion. Okay, only half of the portion of that one. So half of this area means it is parabolic area. So 2/3 of base into height is the formula. So 2/3 base is L by 2. This is L by 2. Okay, and height is WL square by 8. WL square by 8 divided by EI. It's like M by EI diagram. You have to prepare M by EI diagram. Bending moment divided by EI. Okay, so divided by EI. So this is what is theta 1 value. That gives you a standard value that you know very well. For a simply supported beam with UDL slope at the support is WL cube by 24 EI. Okay, so this is how you get theta 1 value. Now the final net rotation of the tendon is nothing but one is hugging, the other one is sagging. So both are opposite rotations, so you have to deduct from one value with the other one. So treating, we don't know the values, that's why rotation due to loads is greater than that due to pre-stressing force. That is the assumption that we are making, means theta due to loads is more than theta due to pre-stressing. So that we have taken. So what happens finally? So this is a rotation that we have, and this is a cable, the tendon profile. Okay, so this is actually the original length up to this point, and this is the extra length that because of rotation. So if you are able to get this value, and we will be able to find the strain value, additional strain. Okay, so what is that value? This is theta. Okay, this theta, and this is eccentricity, E value. So the length of the arc is like this one. So if you just imagine that this is like this one, and this is like rotated. So this is theta, angle of rotation, how much rotated. This is eccentricity value, E. Okay, so this value, that is extra length, is nothing but E into theta. Okay, E into theta. So that extra length is on both sides. So 2 times E into theta is the total elongation of the cable. So if you want strain in the cable is like 2E theta divided by L. Okay, so this is total strain in the cable. If you want stress in the cable, so stress divided by strain is equal to Young's modulus of steel. Okay, so we know strain value, and we know Young's modulus of steel value, and we get stress value. Increase in stress due to loading is equal to Young's modulus into the strain value. Strain is 2E theta by L, and Young's modulus value ES. So ES 2E theta divided by L is the formula to calculate increase in stress due to loading. That means Young's modulus of steel must be known to you, and a small e value, eccentricity of the cable, it depends. So if the eccentricity is more, increase in stress is more. Okay, and theta, if you want theta, you need to find both theta 1 and theta p, and those formulas are like this: WL cube by 24 EI is theta 1 due to loads, and PEL by 2EI is theta P, okay, due to pre-stress. So you have to deduct from one value with the other, that you get theta value, substitute it here. L is the span of the cable. So if the span is more, increase in stress is less, okay, inversely proportional. So eccentricity, if eccentricity is more, increase in stress is more. If theta is more, and increase in stress is more, okay. Theta depends again on loads and all, okay. So these are uh, the formula for finding increase in stress due to loading, right? So uh, just to put it as an example, one case, if you can see. So there is a point here to note: elastic range, if you take for a steel, okay, for example, uh, if you consider for high tensile steel, the elastic value, I mean stress, elastic stress value, nothing but yield stress itself, okay, because you can't clearly identify what is limit of proportionality or elastic limit, okay. So say for example, if a HTS wire is having 1000 megapascal as its yield stress, considering this itself as elastic limit. So if the stress in the steel is less than this 1000, then the stress in steel change because of this load, pre-stress and all, will be very less, and it is almost negligible, okay, right? The stress in steel is more or less constant, and it won't change even though the member hogs, member sag, okay. More or less constant means very little change will be there, and that will be almost negligible if the stress in the steel is well within the elastic limit, okay, right? So that we can explain with this example. So the cross section of pre-stressed concrete is 6 meter span, 100 wide, 300 deep. The initial stress in the tendon is like 1000 Newton per square with eccentricity 50. So sectional area of tendon is given 100 square. Stress is given. Cross section area of tendon is given. So you get P value. So find the percentage increase in the stress in the wires when the beam supports live load 4 kilonewton per meter, and if you want dead load, use gamma. Okay, right? So modulus of elasticity of concrete is given as 36 kilonewton per square. Okay, or 36 megapascal you can take. Modulus of elasticity of steel 210 is taken, okay, just for the sake of calculations, right? Moment of inertia bhq by 12, because it is 100 by 300 is the cross section of the member, right? This is 100 and this is 300, okay, right? Pre-stressing force is like stress into cross section area is like 100 kilonewton. Now get theta P first, which is PEL by 2EI. P is the 100 kilonewton, E eccentricity 50 L is 6 meters, and 2 times Young's modulus of concrete, and I cross sectional property like moment of inertia. Okay, so this is like Young's modulus of concrete, you shall be substituting. Okay, 36 is the Young's modulus of concrete. Like self weight of the beam is like cross section area into gamma. This will give you dead load value, live load value, total you can get it, total load. Okay, and now rotation due to loads. Okay, so WDLQ by 24 EI. Here also Young's modulus of concrete. Okay, right, because you are calculating the rotation of the concrete at that point, okay, where steel is present, right? So this is the calculation. W, substitute for W, length, I mean span 24, E 36, I value, okay. Next, the net rotation, if you see, this is a rotation for pre-stress when pre-stress is acting, and this is rotation when loads are acting. So just the difference is 0.0034 radians is the net rotation. So elongation is like 2 times E into theta, that is 0.34 mm is the elongation in the steel. Okay, so this elongation divided by L, mean change in length by original length, delta L by L, into Young's modulus of steel will give you stress in steel, right? So 12 Newton per mm square. So initial stress is 1000, whereas the increase is only 12 Newton per mm square. If you get it in terms of percentage, so 12 increase in stress, original stress 1000 into 100, uh, to convert into percentage, 1.2% is the increase in stress. So 1% of stress roughly is not a matter at all when you are talking about 1000 Newton per mm square. 1001 is not a matter at all, okay. So this is so you have to be careful when substituting Young's modulus value, where Young's modulus of concrete shall be substituted when you are calculating the rotation of a member, okay. And finally, Young's modulus of steel shall be substituted when you want stress in steel. That is a point to be noted in this problem, okay. Next session we will see uh, the change of stress in steel when with the bonded or unbonded tendons case, okay. Right, thank you.